Simon Tindemans is an assistant professor at the Delft University of Technology in the Netherlands. His research area is statistical risk management for power systems, which covers Monte Carlo methods, machine learning, and aggregate load control. He obtained his PhD in theoretical biophysics and was previously a Marie Curie Intra-European Fellow and Research Fellow at Imperial College of London. The title of the presentation of Simon is Accelerating System Adequacy Assessment using the Multilevel Monte Carlo approach, and I believe that this will also be a live presentation. Simon, you have the floor, and I will let you know when you have 2 minutes to finish. Thank you.
Perfect. Thank you. Thanks for this introduction. Indeed, this is a live presentation. Thank you, Marie-Louise, for introducing the general topic of system adequacy assessment. So everyone who wasn't familiar yet is now. So I will be presenting the paper that I started working on a long time ago with Goran Strbac at Imperial College London, but I'm now at Delft University of Technology. And it is about multi-level modeling for fast and accurate system adequacy assessment. So before starting, let me quickly acknowledge some of the co-workers, former co-workers, other colleagues that have contributed in some way to making this happen and partially funding the research. And let's get to the content. So this is about kind of a standard problem. This is a picture that depicts, I think, in my mind, a standard problem that many modelers and simulators are encountering, which is you have multiple ways of modeling the same thing frequently. And typically the answer is, okay, well, pick one, right? Pick one and move on. This talk is about how sometimes you don't pick one, but you can actually do something smarter. And I'll show you how that works in the next 15 minutes or so. So the context in which I'm doing this is the measurement of risk in system adequacy studies. So typically it turns out that whenever you perform these studies, essentially they all have a similar format. I hope you can see the mouse pointer, which is that you're trying to estimate some quantity Q, which is the expectation of some random variable X. So examples of this are, for example, loss of load expectation in hours, where X then is the number of hours of shortfall that you would encounter in a random year. Or loss of load probability, where X is the binary out state of a random snapshot. You have loss of load or you don't. Or expected energy not supplied, where X is the amount of energy you don't serve in a certain period, for example, 1 year. So that's the context. Now, typically for any system that's not very simple to analyze, one often resorts to Monte Carlo simulation. And that's all based on the Monte Carlo estimator. So here you say, well, the idea is simple. Obviously, we approximate our the quantity Q by the Monte Carlo estimator, which is simply the average of a number of independent random measurements of the thing we're trying to average. So these xi here are these values. And over time, there are strong results that this converges to the right answer, and the long-run error you get scales as a standard error with 1 over the square root of the number of samples. So this is a really nice, simple procedure, very robust, but sometimes this convergence can be very slow. And especially if your simulator is slow, that can be problematic. Okay, so before going into what we did in this paper, I'll first explain quickly the example we're working on. And this is the running example I'll use throughout this presentation. So this is the example of storage in adequacy assessment. So storage is interesting and difficult because, it's interesting because it's increasingly important in practice. There's more and more reliance on batteries or virtual batteries for, let's say, demand response in operational flexibility and therefore in determining the adequacy level of a system. But storage, because it has not only power constraints, but energy constraints over time, typically necessitates time sequential simulation. So you need to really simulate your system as it behaves through time. And if you then on top of that want to implement a proper high fidelity dispatch strategy, this can be computationally very expensive. And that's if you can even agree on one. So the case study we'll use here is a Great Britain inspired system where we calculate the loss of load expectation and expected energy not supplied. So so 2 quantities. And I'm going to here use 4 different models. I don't go into much detail, but let me quickly say there's four kind of models of varying crudeness. On the one hand, we have the no storage model, where we say, okay, let's forget about storage actually, and let's compute the system adequacy of the system without storage. And in this case, actually, we don't need time sequential simulation, and we can simply compute the answer directly by convolution. So we can even skip sampling altogether. On the other hand, in the bottom, number 4, is where we have multiple storage units. Sorry, there's a typo here. It's not greedy operation. It's within a recently published paper with Michael Evans and David Angeli, where we have proposed an expected energy not supplied minimizing storage dispatch strategy. So that's proven optimal strategy for minimizing E and S. But it's a little bit complicated and it needs time sequential simulation. So in between these 2 extremes, we have 2 intermediate models. We have one where we say, okay, let's use, instead of the 27 storage units, the batteries we use in the complex model, let's use a single battery, like an aggregate approximate battery. And even simpler, we dispatch it the same way every day, such that it reduces peak demand in typical peak hours and then recharges again in typical kind of low usage hours. And when operated in this way, this battery essentially becomes a net offset to the demand. And again, we can skip sampling altogether, computed by convolution. And then we have a third model, which actually is sort of a crude approximation of our kind of detailed, correct sampling model, if you wish. And it greedily dispatches all the 27 units in a certain clever order. But there's no guarantees that this is anywhere near optimal, but it's a little bit simpler. So we have 4 models, very crude to very detailed. Ideally, we'd like to run model 4 all the time, but it gets really, really slow. And we know that model 1 is really fast, but it's not as accurate. So that puts us in this picture. We have our 4 models where we have increasing accuracy and more work per sample as we go for all the bells and whistles. All right. So moving to multi-level Monte Carlo. And again, the paper is quite technical. Here, I'll just sketch out kind of at the very highest level some of the big picture and some of the considerations there. So what is the idea of multi-level Monte Carlo? So the basic premise is that you use crude and fast models to get approximate results first, and then you use increasingly accurate but slow models to compute corrections. So you approximate this guy by the simple model plus some difference term, some correction. So that's the essential idea. Let's put a little bit of notation on that. So the setting we consider is where we have a hierarchy of models. So we have models M1 to ML. In our case, we might use 3 or 4, where ML is the best model. And each one of these models generates outputs of the type we're looking at, right? So I can compute the expected energy not supplied, or I should say energy not supplied, with each one of these models and sample them. But what we're really interested in is the expectation of the output of the most complex model. So our quantity of interest is the expectation of the output of the most complex model. Now we can rewrite this, and it's a little bit of trivial mathematics that seems complicated perhaps, but we can rewrite this quantity we're looking for as the expectation of the crude model plus the difference terms added on at the end. So this is called the telescopic identity. And if you look at this, it's basically a basic value here, R0, plus a list of correction terms, R1 to RL. So coarse estimate plus corrections. So now that was multi-level. Let's put the Monte Carlo in multi-level. Well, recall we had this quantity. Q is the sum of R0 plus RL, plus R1 and so on to RL. And we replace each one of these by the Monte Carlo estimate. So now our Monte Carlo estimate for this thing becomes the sum over all these levels of the averages of these differences, where the lowest level is not actually a difference, it's actually the crude value. So we have these little differences here, which measure the difference between the same state measured with different models. So every time we compare how this, for example, for this wind power trace or this demand trace, what does this model say? What does this model say? And we compute these differences. Okay, so why and when does it work qualitatively? The requirements for this are that simple models are much faster than complex models, and that's often the case. Also, that simple models are simple, but they're not necessarily terrible. They often actually approximate the true answer very well, but they can deviate in small and potentially unknown ways. So what you need to do, and again, more details in the paper, are to select an appropriate combination of levels. Which models do you combine? And determine an appropriate number of samples to evaluate for each level. And again, that's in the paper. Okay, so I'm going to compare some results now in the next slide between 4 different configurations. And they're drawn here. There's a little bit of information to take in. Vertically, you have the various model combinations I look at. Now you see for all of them, the EENS minimizing dispatch strategy is at the top. That's the model we want to know. So what we can do is regular Monte Carlo on the left, which is directly only sample from this model. We can also do various other configurations, and I'll walk you through this one, the second, which is a multi-level, where we sample from the no storage configuration, from the difference between greedy and no storage, and then again the difference between EENS minimizing and the greedy model. So we build up the multi-level stack in this way. So I want to emphasize that all of these combinations will give you valid, accurate results, but the speeds will differ, or at the same kind of time spent, some of them will be more precise than others. Okay, so here are the results. On the left, there's a lot of information again here. On the left, you see the 4 various models, combinations that we picked. You see all of them have run for approximately 10 minutes or so. And here are results we get for loss of load expectation estimation and EENS estimation. All of these results within their errors are essentially the same. But what you see here is, I want to draw your attention to this Z, this kind of speed factor. So where we get a figure of 0.1 in some units for regular Monte Carlo. And as we cleverly kind of pick the multi-level stack, we can speed up the rate at which we're kind of getting accurate results to 6.8, which is 66 times faster. So for the same result, simply by recombining models. Now, if you look at this EENS, the difference is even larger. We get a speed up of actually 2,000 times here. Again, simply by making a 3-layer model stack. So that's an incredible improvement that we get. Just want to highlight the code for this is available both on Zenodo as a downloadable package, but also here on CodeOcean as a capsule that you can actually simply run online. So wrapping up, I want to argue that multi-level Monte Carlo is a very natural fit to system adequacy studies. It applies in a setting where where you estimate risks that are associated with some impact X, some random variable. You often naturally have a hierarchy of models where you have a very kind of quick basic model, and then you add all kinds of little items and bells and whistles that make it very, very slow, and often only have incremental improvements in accuracy. And again, I won't go into details here, but it's a very natural setting for multi-level formulation because it's often very simple to generate these joint samples across different models. For example, if you have common inputs like weather patterns or demand patterns that can easily be input into various different simulators. So to summarize, in the paper, not in this talk, there is first, as an aside, a kind of a speed metric for multi-level Monte Carlo simulations, which is not one I was familiar with, but I find it very useful. So maybe you will find it useful as well. And of course, the main point is that multi-level Monte Carlo can provide really, really large speedups. In the storage example here, you see 66 times speed up for the LOLE index, which is a little bit less well behaved, and over 2000 for ENS, which is very well behaved because it's a continuous metric. You can use this method to either reduce computing time or increase accuracy, or both, as you wish. And yeah, work is ongoing to enhance this in various ways, mainly to look at whether we can automatically pick this model stack, right? So you found here these results where I combined various model stacks. Let's say, let's combine this with this and this and this, and we get different speed ups. It would be really nice if one could just make a bunch of models, give it to the solver that would then automatically find the best combination of models. Currently, this is a hand, this is manual labor, and I'd hope to automate this in the near future. So with that, I'd like to thank you for your attention, and happy to answer any questions.
Simon, thank you very much. This was a very interesting presentation, and you really kept the time exactly at the, let's say, desired level. Maybe we give a minute or two to the attendees of the session to type in their questions in the Q&A, and please may I remind you to also type in your affiliation. While we do that, maybe I can ask an explanatory question. If you go back to the slide 15 where you discuss the speed ups.
Yeah.
So I'm a little bit confused, let's say, with the difference between the Z metric, which I guess is the time per sample, which is the fourth column here.
Yeah.
And the run times, because I see the run times are in the end very similar.
Yeah, so what I did is so Z is not directly a runtime per sample. Let me just go here actually. So it's normalized. So I normalize by, so this is so 1 over, so T here is the time spent at some time simulating, and you have this, in the denominator again, the variance of the thing you're measuring, of the your estimate, and on top you have the actual value. Now this is a normalization that allows you to compare runs with different runtimes, right? So as long as you're in the asymptotic convergence, right, which you know it is, when it applies, it kind of is a normal distribution with 1 over square root of n. Anytime you're in this convergence, you can compare points either after 5 minutes, 10 minutes, or 10 hours, and you can normalize in this way. So this kind of automatically is taken care of. Mm-hmm. So it's a little bit more complicated than that. Basically, it is the time in seconds you need to achieve a certain coefficient of variance.
Okay, I see.
That's how it's normalized. And it's nice because it allows you to compare speed metrics also across different quantities. So you can directly compare this Z for LOLE on this side with this Z for ENS. And you can see that in this combination, it's actually this one that is binding for the coefficient of variation, not this one because it's higher.
And so, actually this explains also why the LE metric, sorry, the loss of load probability is much more difficult, because it's the variance that matters. Now, I have another question from Zhao Yuan. Unfortunately, I don't know the affiliation of Zhao. However, the question is, how is the accuracy improvement performance of multi-level Monte Carlo method? Did you compare the results to the single-level Monte Carlo method?
Yeah, sorry, maybe I wasn't clear. So that is exactly this graph. So here on top, you have single-level Monte Carlo method. Now, I want to be clear, I made no attempts to either optimize or deliberately de-optimize any one of these, right? So absolute numbers here can change quite a bit depending on implementation. But for this code, which I just got from one of our other papers, so actually Michael Evans, former PhD, he created this piece of code. I just inserted it into this function and use it as is, basically. So the top here is what you'd get by directly invoking the most complex model. And it has the speed of, so in this case, 0.1. So that is the speed up versus regular Monte Carlo, yes.
All right, thank you. Thank you very much, Simon.